Hello everybody in the Software Engineering CS 401 course. This is lecture number 2. I thought I'd take a moment and step back a bit, and today's lecture is going to be on object-oriented design in general. I noticed from the midterm that some people are not necessarily grasping the concepts of static or class level variables versus instance level variables. And the whole object concept, I think, is a bit confusing for some people. So today's lecture, we're going to step back, take a look at object orientation in a little bit more detail, and then hopefully the diagramming and the object-oriented design with UML will make a little bit more sense to you as well. So today's lecture is going to be number 11, object-oriented design.ppt. And I've got it right here for you. And so let's just take a look here. So it says object-oriented programming or object-oriented software design and Java programming. We're not really going to look at Java programming. What we want to look at are putting the pieces together. Creating a design that is reusable, creating a design that incorporates all of the core aspects of object orientation. So object-oriented design is a technique for developing programs in which the solution is expressed in terms of self-contained objects. We all know that, hopefully, because we've all taken object-oriented programming classes before. So the programmer thinks about and defines attributes and behaviors for objects, and often the objects are modeled after real-world entities. And so UML, Unified Modeling Language, is modeling what you're thinking. So it's a very different approach than function-based programming in C or C++, function-based stuff. So reasons for object orientation and object-oriented programming, well, it provides this, and I think I've given you this acronym before in a previous lecture, but just in case I haven't, I just want to discuss it here again. API, which stands for abstraction, polymorphism, inheritance, and encapsulation, which means we're going to take these concepts and put them on steroids and put them in diagrams, and then developers are going to be able to take these diagrams, the UML diagrams, and translate them into the source code. And so when you're writing the diagrams, it's like writing the source code. And when you're thinking about object orientation and you're planning the software design ahead of time, it's like you're writing it, but you're not writing it. So you can get non-programmers to design some pretty sophisticated software that does some pretty good things quite easily without having to know anything about programming. So yeah, there's software engineering issues, and these are addressing, object orientation addresses it. Okay, so we all know about the class, and the class defines the pattern used for instantiating an object of that type. And we all know that the class generally contains private data, and we all know that it contains public operations, and the public operations are sometimes called methods, messages, functions, member functions. They go by a lot of names. Object types, the Java class is the object type. It's the data type for the object. So when we create a class diagram, we're creating the data object types. An object diagram is showing a higher level view of the class diagram, just showing the objects. When you create the definition of a class, you're defining the attributes and the behaviors for the new type. The attributes are the data members, the behaviors are the methods, or the behaviors, aka the methods or messages. So you define a class. It does not actually result in an object. As you know, you make instances of objects. I think we've all gotten past this stage of our understanding because everyone has taken a C++ course. So you've created a class and you've made instances or instantiations of objects. And hopefully you've been exposed to the concept of inheritance as well, where you have a superclass and you have a subclass, and a subclass can be a superclass and vice versa. And inheritance enables us to define a new class called a subclass that inherits the properties that already exist in the previous class. And we've seen it in C++ and also in Java with the ability to carry over data from the previous inherited class and methods. And we have looked at, and we're sort of interested in kind of making sure you are good with the concept of overriding and overloading as well today. But we take what we have in the superclass, we subclass it, we make it more specific, we derive, which is called deriving a class, we add properties to it, to make it more specific and to make it more less general. For example, we can have a car object, and then from car we can inherit a BMW, or we can inherit a Toyota, and add different attributes to it to make it more of a BMW or more of a Toyota. So the class being inherited from is the superclass, and the one that's inheriting the properties is the subclass. All right, so defining the object itself, an object-oriented program consists of many objects. The program itself is nothing more than a definition of all of the objects. The objects are composed of identity, states, and behaviors. So the identity is, generally speaking, is the name of the object. The states are the attributes or the data that the current object the data that belongs to the current object, and the behaviors are the operations or the methods. Those are the three sections of the box that you're filling in when you create a class diagram. So identity of the object distinguishes it from other objects. Failure to recognize the difference between the name of the object and the object itself is a source of many errors. It is, especially when you have an object that's called print and it's doing scanning and it's doing other things outside of printing. And the major mistake most people make is they put the controller in another object. So they either put it in the driver or they put it in another object that was created, and it's really doing controller behavior, and it's not even like behavior that's associated with that object. So you want to make sure you've identified your objects properly, and each object is a single standalone object that doesn't contain other objects inside of it. Now it can, and when you get into more advanced object-oriented design, you'll discover that you can stick objects inside of objects. But for the purposes of this demonstration here, or this lecture, consider you're not going to nest objects inside, and each object should have its own unique identity. Now the states are the properties or the values of the data that the object is holding on to. A property is inherited or distinctive characteristic, trait, quality, a feature. It contributes to making the object unique to what makes the object unique is its data and its member functions. So the states are, is the elevator turned on? Is the elevator turned off? It's basically controlling the current environment of the object. And, just imagine this as a real world object. The states would be what's happening to it right now and what's going on with it. So we'll use the word attribute or data member to refer to the states of an object. So properties and the elevator example. So properties might be the elevator traveling up or down, a vending machine accepting coins, how many coins are in the vending machine, clocks that indicate the current time. The values, associated with, let's say, an elevator going up or down might be the current floor, the number of coins deposited in a vending machine, or the number of minutes since the last hour, perhaps for the clock example. So the behavior is how an object acts or reacts in terms of its states. So the behaviors are, what is the object able to do? Can it lift something? Can it move the floor from the first floor to the third floor? An operation is some action that the object performs upon another object to elicit a reaction. So we'll use the word method to describe object-oriented behavior in C++. Well, we also use the word method in Java. So invoking a method causes the behavior to take place for the most part. So this, whether or not we're in C++ or whether or not we're in Java, the method is the messages or the functions. So the classes in general are definitions or blueprints used to create the objects, descriptions of the objects. Okay, so in this example, we're going to make cars. So to make a car, the manufacturer must first have a design from which to build the first car. And then once the problems have been worked out and the design is perfected, then we're going to build other models of cars from that. So the object is the instance of the class. So if we have a class definition called car, we can think of Audi, BMW, and Corvette as each being an instance or object of the class car. So they're types of, each type is a type car, which gives us our is-a relationship. So in Java, we have an is-a, so a car or an Audi 6, or well, these are old models, a BMW Z3, well, it's not too old, is an instance of or is a car. So notice that all objects are the same type. All objects are cars, but they're different inherited versions of the car. So they're all of the same object type. And so if they are all of the same object type, then they can all be stuck in the same array together, which is something I was trying to test for on the midterm, and about 50% of you weren't able to figure that out, that elements were elements and that they weren't like, you can just make them all the same because everybody was an element. Everybody was an instance of the same object. So an object is an instance of exactly one class. So the Corvette cannot be an instance of a car class and also an instance of a plane class at the same time. This is single line inheritance. We can bring in multiple lines by using interfaces in Java or using multiple inheritance in C++. So we can make an object that has, in C++, you can make an object that inherits from two other objects. I could make a Corvette, and it could be an instance because it could actually incorporate or inherit from a car as well as a plane. That doesn't make any sense in Java. It does in C++ for some strange reason. But if we're thinking about Java, an object can only be exactly one class. It's one class type. So a Corvette is a car. It's not an airplane like it is in C++. An instance of a class, an object, belongs to the particular class. So the Corvette is a car. And so Corvettes belong to the car class. Once a class is defined, you can create as many instances of that class as you want, objects from the class. We know about that one. Once a blueprint is completed for a 2004 Porsche 911, that is an old car. That's a couple 16 years old. So you can use it to assemble other instances as well. So we have our properties or our behaviors. Our properties are our variables, which describe the essential characteristics of the object. For example, for properties of a car, we have color, model, make, how many doors, transmission type, direction of movement. For behaviors, they are methods that describe how the object behaves and how the properties may be modified. Braking, changing gears, opening doors, moving forward, moving backwards, those would be behaviors. So instance variables are instances or objects. The class definition includes parameter definitions or properties that represent data that is held by that particular object alone. So Joe's car has 4 gallons of gas in it. Well, John's car might have 10 gallons of gas. Instance variables are variables that are held by the instances of the objects. The amount of gas in each one of the car may change without affecting the amount of gas in any of the other cars because all the instances hold their data separately. So the combination of all the values for the instance variables are known as the object states. So all the values for all of the different things. So these are instance variables. We have a car, and the car might have a data field called maximum speed. And you see all 3 instances have different maximum speeds. They're holding different maximum speeds because these are instance variables that are held separately by each instance of the object that is created. So we call them, and the purpose of today's lecture is to give you the vocabulary so that we're all on the same page with stuff. So that was an instance variable. Now, where most people kind of ran into problems on the midterm, which is why we're doing this lecture today, is you didn't quite get the class variable. The class variables are definitions, or the class definitions may also hold parameters that represent data that's shared by all instances of the object. These are class variables. We can have class variables and we can have class methods, just like we have instance variables and instance methods. In this case, the car class defines a maximum allowable speed by law. So we have a max speed, and it will be the same for every single car that's created. So in the car class, the max speed in here at the class level holds on to the value that's being accessed by all of the instances. Now, we don't actually access it or change it by any of the instances. We have to change it by the car. So that's how we did in the midterm. Car dot whatever it was, is what the name of the method, excuse me, is what was run, not an instance dot and then the name of the method, because instances don't run it. The car owns this class level variable. So if you remember, instance goes to each one of the instances. Oops, I'm going to have to go this way. Instance variables belong to each one of the instances of the objects. The class level variable is just a member of the class. Now, it's not a member of every single one of the instances, but the instances can affect the value, but it's done at the class level. So that's a class variable. So that's used to keep track of things such as how many instances of a class exist. So let's create a counter and record how many cars are in the garage. If we do that, and this is one of the purposes of the class variable, is to keep track of, let's say, for example, how many cars we have. So the number of cars is equal to 3, because the constructor for each one of these is incrementing this. And it's causing, when the new instance of this object is created, it's using this template because it's inheriting from car. And car constructor, which is the super constructor, is incrementing this. So if I were to write code to increment a counter, I would stick it in the car class. It could be abstract, it could be a regular class. And then each one of the classes that inherited from this particular class would run super. Super is going to run the default constructor. The default constructor says number of cars plus plus. And so each car is incremented when each instance of these methods, each instance of these cars are created. So that's a class variable. So messages. So for objects, and then here we have for humans, which means the object-oriented terminology is on the left and English is on the right. So the object to whom the message is being sent is who the message is for. The name of the method of the object is what do we want the person to do. And any parameters or variables needed, those are the parameters and what information is needed to do it. So it's kind of the translation between object and humans in terms of what the methods are actually doing. This is Audi.turn on hazards, the name of a method. So in order to process the messages, an object needs to have a method defined for the requested task. We all know about this from the beginning C++ course you took. The method is a small, well-defined piece of code, completes a specific task. So for our previous example, we need to define a method to turn on the car's hazard lights. So we put the method in here, turn on the hazards, and then each one of the instances can run it. This is an instance method. So each one of the instances that are created of the car type can run this method. You don't have to repeat it in here. It already has access to it. So these are the two items that are being accessed. These two items up here are data class level variables, class level data. If we were to create a method like what you're supposed to have done on the midterm, you would have to create it as static, which makes it class level. So class level data is modified by class level methods. Instance level data is modified by instance level methods. So these are everything in the instance is an instance category. Everything in the class is both instance as well as class. So just keep that in mind. If you want to modify static data, you have to do it in a static class. Static means class level in Java as well as C++. It means the same thing, but some people didn't learn this in C++, I guess. But class level is called static. Why they call it static, I have no idea. Well, static probably because it doesn't change. It's the same for each one of the instances. So I don't know. Instance methods. So each class can have its own specific instance messages. They could only affect the object's parameter for that instance. They don't affect everybody else. If the BMW has 4 gallons of gas and someone puts 6 more gallons of gas in his or her car, the car now has 10 gallons, the amount of the Audi and the Corvette and all the other objects have not changed. Only that one particular instance has. So we have an add gas method just added to our our chart. This, by the way, minus a couple of lines in here, is the class. This is the class diagram. So this is the class diagram. It would be showing this way in UML. So if you were to show the inheritance, you would actually draw a line. This would be a box with 3, and we saw that in the previous lecture, 3 sections. The 3 sections here are the name. We don't necessarily have to repeat the word car. This is for illustrative purposes. But then you have another section for the data, and then another section for the functions. Those are the 3 sections of the class diagram. This is kind of a makeshift class diagram done for illustrative purposes. The inheritance would look exactly like this, though. We have the main class up here, and then we have the inherited classes that come from that. And then inside of the inheritance, and this is just showing you instances right now actually, but it is also showing you the class, you can add more data. And this does not have any adding because we basically just created 3 instances, and this is demonstrating an instance. But if you were to turn this into a class diagram, you would do it in a very similar way to this. Draw the lines in here, or use the template or the drawing tool, and then add data to this. And then you would be making instances of these classes. These right here are just instances of car, but maybe you get the point, maybe not, who knows. Methods. So it's also possible that you want information about it, and you want it to define a method that sends or returns a message back to the requester. So you need to know how much gas is in our car. So these are like the setters and getters. So here's some methods here. Turn on, get gas level. This is C++ notation, by the way. Add a class from, here's another add gas. So these are just showing you methods. We already seen setters and getters. And everyone was pretty clear on the setters and getters concept. When it comes to class methods, the class methods are used to get and manipulate the information about the objects created from the class level. Typically, class messages are changing class variables. Typically, they don't actually have to. You can create other class methods that do other things. So each time you want to move a car in or out of the garage, you can add or subtract 1 to the number of the cars, like car in and car out. Also, you may want to know how many cars are there in the garage. Get number of cars. So these static class methods can modify the static data, but they can also do other things. So just keep that in mind as well. Just because it's a class level doesn't make it any different. It's not restricted to just working with static class variables. It can work with anything. All right, so when we write object-oriented programs, first one, we must define the class like car, and then when the program is running, we have instances of it, objects that are created after that. So object orientation in general, the benefits of it is that it gives us and allows us to create modularity in our programs. And so an object has a public face to it that it uses to communicate with other objects. But other objects cannot directly access its instances, its instance variable. That's what's called information hiding. So let's talk about modularity for a moment or two here. It's not on the slide, but I can explain it to you. We use interfaces, and they're actually called public interfaces. We saw that on the midterm as well. The public interface provides standard methods for the class. And so we do that so that we can give all classes that abide by the interface, that implements the interface, have implementation of these methods. That gives us the information hiding. We don't have to go back and wonder, how was the method implemented? We just run the method. An example of that is the toString. So once the toString is created, and we know that that toString is there, and the toString is not coming from an interface, it's coming from the object properties that are inherited automatically from object in Java. And so that toString method, once we implement it, we just run it. And we know that all objects have a toString method, whether it's overridden or not. Most people would override it so they can print out something specific that is relevant for the object and not the memory address. But we all know that the toString exists and we can run it on any object. That's the information hiding. So we don't have to worry about how it's implemented, we just run the method. And so when you get to things like Android that uses Java, it's heavily into the interfaces. So like on-click events and things are all incorporating interfaces. Those interfaces allow you to just run a method and the method works because it's, base functionality has already been implemented for it. And so we can run the same method on multiple objects that all abide by the same interface, and we know what they are. So it gives us a little bit of modularity as well. So if you separate the objects out into their separate components and you run these objects with in groups, like one object calls another object that calls another object. It doesn't matter which programs are calling which objects. The idea is you have this repository of objects and you stick all of the objects in the JVM or on the system, regardless of what platform you're running this on. And objects that you wrote years ago can be called from current programs. So that's really the modularity part of it. And the idea about Java is the reuse. So you might already have an object that's created in the system that's been around for years, and you're just writing a new program. Well, the new program can use that object. So there's no limit. In a C++ program, when you create objects, they're encapsulated inside an executable code. So you compiled the program years ago. Inside of the .exe file are these objects, and these objects are, kind of time capsuled. They're stuck in stone. In a Java program, the objects are all separated out in their own .class file. They're not in a time capsule. They can change. You can recompile them anytime you want, or you can just leave them in there and then reuse it. Reuse it as many times as you want without having to rewrite it. So there's a lot of rewriting and recycling in C++. There's a lot of reuse and information hiding in Java. And the information hiding part of it is the fact that we don't have to worry about how the class was implemented. We don't even have to touch the class. We just use it because the functionality has already been implemented. And it gives us modularity and it gives us reuse, which are really good object-oriented features. So information hiding, the interface to the object or the class, is the list of public data members or methods. And so we've seen an interface. You've written a couple for the midterm. You know what those are already. They're just prototypes, method prototypes, and you can put data in there. But for the most part in Java, you just have the methods in there. And the interface, we don't know how it's implemented. A good example, actually, of an interface is system.out.println. We just use system.out. We don't know how it's implemented. There's an interface that tells us system.out does this. But there's a different system.out for all the different platforms, for all the different versions of the JVM. So the interface defines the behavior of the class to the outside world or to other classes and functions that may access these variables of that class type. So the implementation of your class doesn't matter outside of the class, only the interface matters. And all you really need to do is provide the interfaces. And once you have the interfaces, you just use the interface. You don't have to worry about somebody else's code. So if you imagine 4 or 5 different programmers all writing the same application, and what are you going to do, share all the code that they're currently writing? No, you just come up with interfaces. Everybody has an interface for their section. And other programmers, they look at the interfaces. They go, oh, there's this method. Oh, there's that method. I can call this one. I can call that one. It's kind of like if you were doing web development. Someone said, oh, we're using a MySQL database, and here are the tables that we have. So you just look at the table diagram, or the ERD, entity relationship diagram, that shows the tables, and you don't have to have access to the MySQL database. You don't even have to touch the data. The diagram and the interface to the tables is going to show you what is in the tables and where the data is stored. It's the same concept for object orientation. So in information hiding, you can change the implementation and nobody really cares as long as the interface is the same. So if for reuse and for software development, we leave those interfaces the same. So the interface is what you really have to focus on in getting those correct, because those will never change, but the implementation will always change. So you can use other people's classes without fear, because that's how they're interfaced. So let's talk about polymorphism, the ability of different objects to respond to the same message in different ways. That is polymorphic behavior. Now, there's nothing else in the slide on that one. Java supports polymorphism at a higher level than C++. And in one of the UML diagrams, you can actually diagram the polymorphic behavior. And it's a pretty simple diagram, actually. The polymorphic behavior gives us our overloading and our overriding, but it also gives us our identity states. So the concept of referencing in Java changes the state or changes how we're treating the object. So for example, if we treated the object as a car, so we created an instance of a BMW and assigned it, and I've gone over upcasting and downcasting, which I'm sort of describing right now again. If I create a new object of a car and I created it as a BMW and I cast it to a car, which means I'm referencing it now as a car. I'm going to get the car methods and the car behaviors because I'm referencing it as a car. If I referenced it as a BMW, then I'm going to get the BMW stuff. And that's how objects can kind of morph. And polymorphism is supported through object identities, which are supported through references to the object. So how you're referencing the object is part of the polymorphic behavior. We also have the ability to cast data and to cast objects to object as a generic object type so that we can use all of the objects together as the same object, because all of the objects in Java all come from object, and so they're all able to morph into that. All right, inheritance in Java is the same as what you learned in the C++ class. You can create a new class that inherits from an existing class. We know that there's a single line inheritance in Java. There's a multiple line inheritance in C++ because C++ doesn't support interfaces. Java supports the interface. So you might say that it's easier to build projects in teams using Java than C++ because you have that interface to rely on. So you can add new methods and members and data members and methods to the particular subclass that you're creating. You can replace methods. The new class is a specialization of the existing class. So as the classes in Java are organized into a class hierarchy, there's another diagram in UML that shows the hierarchy. And so what I'm trying to do is sort of expose you to a little bit more UML stuff too. So all of the concepts that I'm talking about in this lecture today, there's a separate diagram for everything. So there's a separate thing that shows you class versus instance. There's a separate diagram that shows you objects, a separate diagram that shows you just classes, a separate diagram that will show you the inheritance. And the inheritance just shows you the hierarchy, the highest level classes down to the lower level classes, and how the data is added and how the methods are added. So you can document this in a diagram. You don't have to create an inheritance diagram for this class because it's pretty easy actually. But imagine being able to look at this and see the hierarchy and know which classes are in the hierarchy and what was added at each level and what each level contains. It allows you to take an existing hierarchy, kind of get a picture of it, instead of going through a directory of class objects. So the reason why the inheritance UML diagram is used for the most part is when you have a really large project and you've got like thousands of classes, it's hard to tell how they all fit together. What are you going to do? Go back and spend a month or so just trying to figure out, reverse engineer it, try to figure out how the classes fit together because they all should be in a hierarchy. So the picture of how it fits together says 1,000 words. I mean, you can just look at the picture and you can go, oh, there it is. There's where I want to inherit from. That's what I want to do. So the Java docs, show you the inheritance as well, but it's a little cryptic. So the higher level classes are superclasses, lower level ones are subclasses. We kind of know this already. And so inheritance allows us to use another quality of object orientation called reusability. So reusability is the ability not to have to reinvent the wheel, to take a class that has already been written and then just extend from it. So if you extend from it, you inherit from it. And if you're inheriting from it, you don't have to rewrite it. So reusability as an object-oriented feature is supported by inheritance because we just use what we have. Here's an inheritance example as well. We know this from C++ as well as what we've looked at so far. And I think I gave you the shape example perhaps in the first week of class or so. But just to reiterate the point, the base class's shape represents abstract notion of a shape. Derived classes could be rectangle, circle, triangle. An object that is a circle is also a shape. So a car is a car. So if we define a new class called BMW that contains the car parameters model, color, engine size, then we created a subclass of that. And this is what the inheritance diagram looks like. Noticing that there's an arrow, and this is a UML diagram, by the way. It's just missing the lines. So we have a car on the left and we have a BMW on the right. And the arrow goes this way, which means that the BMW was derived from or extends car. Some people put the word extends here, some people leave it out, but you got the arrows that go in between, and these are, you know, the same that you had before. You have the identity, states, and behaviors going on here. You have the class level stuff that's in here. We had maximum speed, if you remember, and gas level. We have model, which came from gas level and maximum speed over here. We did not inherit, we don't inherit the class level maximum speed. We have model, color, and engine that were added to it. And then we have the methods. Now, in the modern day inheritance diagram, you don't separate out the new from the old. You just add the new. So if this were really an inheritance diagram, we wouldn't see these guys from here. The inherited members, we would only see the new ones that were added to it. There's an assumption that the inherited ones get in here too. So we can define two more classes, the Z3 and the 3 series sedan. So we can add different things to each one of the classes, like a soft top or a hard top, number of doors. So we add different variables to it. And here's another class diagram where we have a car, and it extends from, it's called BMW. It extends from car. And then from BMW, we have two different types of BMWs. We have a Z3 and we have a 3 series. And those arrows are going up to BMW. So that's really what an inheritance diagram looks like in a nutshell. Some people put the inheritance in the class diagram, and you can actually have a combination class diagram that's also an inheritance diagram. You just add the symbols in for these really bold arrows here, which is showing you the symbols for the inheritance. So the direction is these guys are coming from here, this guy's coming from here, and these guys are coming from here. So the direction of the arrow shows the superclass, goes from the sub to the super. So we have different views of the class. We have the class as views as a sort of contract that allows our instances and tells our instances what they can and cannot do. So it's possible to distinguish between the outside and the inside view of the class. The interface of the class provides its outside view. The emphasis is on the abstraction. The implementation of the class is its inside view. So you might think of the interface, the Java interface, as the outside view of the class. So you're looking in instead of inside out. So anyway, we know about the access. I'm just going to briefly mention this. You can put this in the diagram. It's generally not using these words. We have plus and minus. That's used for private and public and private. And then in some of the diagramming tools use an asterisk for protected. But most classes provide the 3 levels of access. The public, the private, and the protected. These are put into the diagram generally not with words but with symbols. So you'll see pluses and minuses and asterisks in the diagram. And so you follow the diagramming tool, but you can specify the public and the protected and the private. I'm going to assume we know the differences between these already, that the public data is can be accessed outside of the class directly, that public stuff is in the interface, and that the private is inside of the class and is for internal use only. And then protected, we've seen is visible to the derived classes, but not to the public interface or to the public driver. So we have the special member functions. We're familiar with those already, the constructors. Those can also be put in the diagram, but most people would leave them out. They're called when the object is created or instantiated. So there might be any number of constructors taking on any number of arguments. C++ does have the destructor that can be put in there. So it's called when the object is eliminated. Yeah, not in Java. So accessing the data members are usually available through the methods. Just like C++, you want to make the data private. When in doubt, make it private all the time. And then use the member functions, the public member functions, to access the private data. So public data members can be accessed by other functions using the member access modifier, the dot, just like C++ structure, or just like C++. So accessing class methods within other class methods, a method can be called just like a function. So outside of the class, the member functions can be called only when referencing an object of that type, that class. So if I have a class method and that class method is inside of car, I don't do it from the instances, I do it from car dot, the name of the method. So it's from the class itself. Static methods is a class method that can be called without having an object as well. So methods can't access non-static data members. They don't exist unless we have an object. So, all right, so we know about static. Kind of covered this already. Data members that are static must be declared and initialized outside of the class at the global or file scope. They're not done with instances, so they're done outside of the instances. All right, okay. That's a foo constructor that takes, and the word static is used. So we already know that. Okay, so here's the two programming paradigms we got going on here. We have the structural procedural program on the left. We have the object-oriented program on the right. We see function, we see object, with operations and data. If you haven't gotten the point yet, its object orientation is very similar to the old style functional programming, except for we don't write functions, we write objects instead of functions. So that's what that slide is there. It's basically talking about. All right, so object-oriented programming, we have language features such as data abstraction, inheritance of properties, and dynamic binding of operations to objects. Well, all right, that's a lot of jargon of stuff we've already covered, so I'm going to give you the vocabulary here. When it comes to definitions, the object-oriented programming term is on the left, the Java equivalent is on the right. So an object is a class object or class instance, and what I'm doing is just giving you the vocabulary. The instance variable is the private data member, the method is the public member function, the message passing is a function call to a public member function. So what exactly is that object? It's the set of methods, the public member functions, the internal states or the values, operations, and that's what goes into the object diagram. Here's an inheritance diagram showing you, and this is a pretty good one, vehicle with wheeled vehicles and boats, and cars and bicycles that are part of wheeled vehicles, 2-door and 4-door. So every car is a wheeled vehicle because it comes from the wheeled vehicle hierarchy. A boat is not a wheeled vehicle. So it's kind of showing you the hierarchy from an inheritance perspective. And you can write this in a UML diagram. So from our inheritance, we know this already, and this is kind of review or recap on it. The base class and the derived class. Don't really need to go through that again. Or the composition. Yeah, that terminology I gave you already in red. The composition, perhaps I have not given you yet. So it's a mechanism by which the internal data or the states of one class includes the object of another class. Composed of, or composition, or containment is what they call it. This class car is inside of or contains a wheeled vehicle as well as a vehicle. So it's basically another word for the inheritance. Here's a time card class. The time card has a time object inside of it, as mentioning before. We have the private data we have an ID, a timestamp, and then we have a more data that we can stick inside of it. Here's another object that's inside of it, which would be a time, would be a print, or would be a timestamp actually inside of it. Basically showing you that you can put objects inside of objects. This has a time object inside of it. The time object has hours, minutes, and seconds. This is the object here that's inside of this one. So we can nest objects inside of objects. So constructor rules for the derived classes, they work in reverse order. Same thing that we had in C++ at runtime. The base class constructor is implicitly called first before the body of the derived class constructor executes. The first line, as some people didn't remember, the first line of the derived class should run the base class first. So that's why you put super as the first line, because super runs the base class constructor, and then the derived class constructor runs next. So if the base class constructor requires parameters, they must pass them back to the derived class's constructor. So you go super, and then inside of super, you put the parameters that belong to the base class so that the derived class can collect them, super them back to the base class. The base class can invoke the constructor, run, and then the derived class constructor runs next. So the constructors run in the order of the hierarchy. A car will be created before a BMW class, and so if BMW takes on information that's needed by the car, we super it back by using the word super. It's the first line of the constructor, any constructor. It could be the default constructor or another one taking on any number of parameters. We super it back so that it goes back to the base class, because the base class object is always created first, and then the derived class objects are created second, third, fourth in the order of the hierarchy. So the order in which the constructors are executed, I just described that. This slide's going to give it to you. So given a class X, if X is a derived class, its base class constructor is executed first. Next, the constructor of the member objects, if any, are executed using their own default constructors, if none is specified. Finally, the body of X constructor is executed. If you don't put super in, it runs by default in Java. It doesn't run by default in other object-oriented languages, so it's always a good idea to put super in there, because it also reminds the programmer in the future, if someone's looking at the code, that we're not sending anything back, or if we are sending something back, this is what we're sending back. If you need to send data back to the base class and you do not put super in, the data will never make it back to the base class. So the only way that you can send the data from a derived class constructor that's collecting it to a base class is to put super in there. And so super will allow you to pass it back. They call it super back or supering back because you're passing the information, the data members, back to the base class so that the base class has access to it. Because that one is always going to initialize first. So if it runs first, you need to initialize it somehow. Okay, so I did this lecture, and as I mentioned in the beginning, I felt like I was backtracking a little bit, going back to some basic concepts, because I have had some questions about creating diagrams in UML, creating class and object level diagrams. And the concept is you know the concepts already. You know how to divide things out. You're using this design pattern. And so you need to kind of sort of think about, and in the diagram, you can specify things as being class or being instance level. You can specify constructors. You can specify public access and private access. You can specify what the data is and what the object methods are. It's all the information that I just talked about, which is the core object-oriented design concept. And so if you use this object-oriented design concept and think about these concepts while you're making the UML diagrams for the mine shaft pump, you'll get a better understanding of how you're supposed to put the program together. So that assignment about the mine shaft pump sensor, whatever, controller, is all about thinking abstractly on how you're going to solve the problem and how you're going to break everything out. And you really do need to kind of think about your object design. And I can't really tell you how to do it. It's kind of something you have to figure out on your own. And then you probably can come up with about 3 or 4 different designs. Who's to say one's better than the other? But it's kind of like painting a picture. 2 people are going to paint a different picture of the same of the same concept, and it's going to look different. So I hope this lecture sort of helps you go back to basics and sort of think about object orientation from what it actually is. And it doesn't really matter what programming language you're using. The concept of the objects is the same. Again, this, just in case you want to look at this on your own, it's number 11, object-oriented design. So I hope you've enjoyed the lecture, and hopefully you're staying inside and you're staying safe in this crazy time that we have right now. And I will see you again for another lecture. Thanks for watching.